Welcome to Proving a Quadrilateral is a Parallelogram by Mr. Pi the Math Guy. And the title of the lesson really lets you know what we're going to be taking a look at. We're going to be proving that a quadrilateral is a special kind of quadrilateral today called a parallelogram. By definition, a parallelogram has opposite sides parallel. So let's take a look at how to complete some proofs and work with some problems involving special properties of parallelograms. When you first start studying new shapes, we have to prove a lot of the theorems before we use them, or we should prove them before we use them. Here we have the theorem, if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Here we're given what looks to be a parallelogram, and we're going to prove that it is, but a quadrilateral WXYZ, and we are asked to prove that it is a parallelogram. And what we are given is that the opposite sides are congruent. So we'll make our first statement, and our first statement in any proof is just our given. So in this case, that segment WX is congruent to segment ZY. Now that I've written that into my statement, I'm going to mark it here that WX is congruent to ZY, and the other statement is XY, or segment XY, is congruent to segment WZ. And we will mark those congruent. Now that I have that written into my two-column proof, let's talk about the direction where this proof is going to go. To prove that this is a parallelogram, we have to prove that segment, or side XY, is parallel to side WZ. Then we have to prove that side XW is parallel to side YZ. To prove lines parallel, we have to focus in on the special angles formed by parallel lines in a transversal. That would be alternate interior angles, alternate exterior angles, same side supplementary, or same side interior angles or supplementary, things like that. And a lot of times the proofs for parallelograms have to do with alternate interior angles. For example, if we take a look at side XY and side WZ as our parallel lines, and we'll mark those with this red dash line just to give you an idea. And this is our transversal. Alternate interior angles in this case would be right here, which I'm going to label angle 1, and right here, which I'm going to label angle 2. So to prove that line XY is parallel to line WZ, I need to prove that angle 1 and angle 2 are congruent. On the other side of that, if I look at side WZ being parallel, or what we hope to be parallel lines crossed by a transversal, and WZ, the angles that we're going to need to prove congruent to one another are the alternate interior angles here, which would be right here, which I'm going to label angle 3, and here, which I'm going to label angle 4. So we need to prove those two angles congruent to each other to prove that these sides are parallel. Well, to prove that they're congruent, we're first going to have to do a triangle proof. So let me get rid of these red lines. And now we can start our proof, because ultimately what we have to do is prove angle 1 congruent to angle 2 and angle 4 congruent to angle 3. And to do that, we're going to prove this triangle on the bottom, triangle XWXZ, and then triangle ZYX congruent to each other, then use corresponding parts of congruent triangles are congruent. So the first step to proving these two triangles congruent is going to be to prove that XZ is congruent to itself by the reflexive property. Segment XZ, not XY, but XZ is congruent to segment XZ, and that's because of the reflexive property of congruence. Now that we have, and if we look at the top and bottom triangles, if you will, we have side, side, side. So we can make this statement the triangle XYZ is congruent to triangle ZWX. And that's by the side-side-side postulate. Triangle congruence, side-side-side. Now that we have the two triangles proved congruent, we can prove that the angles, angle 1 and 2, and then angles 3 and 4 are congruent. And we'll do that in red. Actually, we're going to do that in blue. So the fourth step is going to be to say that these are congruent. So angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4 because of corresponding parts of congruent triangles. Corresponding parts of congruent triangles are congruent. So let's mark angle 3 congruent to angle 4. Now what we can say is that the opposite sides are parallel to one another. We can say that XY is parallel to WZ. So segment XY is parallel to segment WZ. And remember, that's because angle 1 and angle 2 are congruent. And the reason for that is the alternate interior angles theorem. If the alternate interior angles are congruent, then the two lines are parallel. The other statement we can make is XW is parallel to YZ. And again, that's for the same reason, the alternate interior angles theorem. So we have the opposite sides now marked congruent, or parallel, not congruent. That's what these arrows mean, that they are parallel. And since we have opposite sides parallel, we can state that the quadrilateral is a parallelogram. So in this case, WXYZ is a parallelogram. And that's because of the definition of parallelogram. Again, to review, I proved the two triangles were congruent so that I could prove the angles, which were alternate interior angles, were congruent to prove the sides parallel. This second theorem that I'm going to write a proof for today reads, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Again, a parallelogram proof, or proving a quadrilateral is a parallelogram. In this case, since we're told that if the diagonals of a quadrilateral bisect each other, our given matches that. It tells us that the diagonals, diagonal WY and XZ, bisect each other at E. So we can go ahead and write that into our given. That segment WY and XZ bisect each other at E. Now, that's our given. Much like the last proof, parallelogram proofs are really going to be dealing with proving the opposite sides are parallel by using alternate interior angles theorem. So to identify here, if we take a look at sides WX and ZY, that's one pair of sides that we need to prove parallel. Alternate interior angle would be here and here, what I'm going to label angle 1 and angle 2. If we can prove those two angles are congruent, then WX and ZY would be parallel. If we take a look at the other sides, the other pair of opposite sides, XY and WZ, the alternate interior angles we're going to be working with are going to be here and here, 3 and 4. If we can prove those congruent, then segment XY is going to be parallel to segment WZ by the alternate interior angles theorem. To prove them congruent, we're going to use a triangle congruence proof. So let's get proving angle 1 and angle 2 congruent, angle 3 and angle 4 congruent. The second step of our proof is to actually say that XE, or segment XE, is congruent to segment ZE. We'll mark those congruent now. And the other part of that is that segment WE is congruent to segment YE. And that's because of the definition of segment bisector. So we can mark these two congruent to each other. The third step is to mark the vertical angles congruent. And here we can say that angle XEY is congruent to angle ZEW. And we can also say that angle XEW is congruent to angle ZEY. And that's because of the vertical angles theorem. Now what we have is that we have this top triangle, triangle XEY, and this bottom triangle, angle ZEW, congruent to one another. And that's because of side angle side. Then we also have the left and the right triangles. So triangle XEY is congruent to triangle ZEW, and triangle XEW is congruent to triangle ZEY. And the reason for that is the side angle side. Again, it's the top triangle congruent to the bottom triangle and the left triangle congruent to the right triangle. Now that we have that established, what we can do is we can now establish that angle 1 is congruent to angle 2, because angle 1 corresponds to angle 2 in the left and the right triangle. So we'll be able to say that angle 1 is congruent to angle 2, and for the same reasons, angle 4 is congruent to angle 3. And that's because of corresponding parts of congruent triangles are congruent. Now, here's the cool part. Angle 1 and angle 2 are the alternate interior angles to side WX and ZY. So now we can say that those sides are parallel. We can say that WX is parallel to ZY. I'm going to mark that with a single orange arrow, meaning that these two are parallel. And we can also say that the top and bottom lines are parallel because angle 3 and angle 4 are congruent to each other, which are alternate interior angles. So side XY is parallel to side WZ. And the reason those are parallel is because of the alternate interior angles theorem. Now finally, now that we have opposite sides of this quadrilateral parallel, we know by definition that the quadrilateral WXYZ is a parallelogram, and that's because of the definition of parallelogram. Here we have two more theorems in this video geometry lesson that we're not necessarily going to prove in the video. These will be left for my students to complete as exercises in or outside of class. The first theorem here is if two pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So if we can establish that the opposite angles are congruent, then we can conclude that the quadrilateral is a parallelogram. The next theorem here is if one pair of opposite sides of a quadrilateral is both congruent and parallel, then the quadrilateral is a parallelogram. So here, if we can identify that just one pair of opposite sides are parallel and congruent, then we conclude that the four-sided figure, or the quadrilateral, is a parallelogram. Continuing our work with parallelograms, we have here example 1 where it asks us to find the values of x and y for which quadrilateral ABCD must be a parallelogram. Well, for this particular example, quadrilateral ABCD, we are given information about the diagonals. And for this shape to be a parallelogram, the diagonals bisect each other, which means that this right here, 8x plus 12, must be equal to 10x minus 24. So we can write an equation from that. 8x plus 12 is equal to 10x minus 24. Now the other equation that we can write comes from the other diagonal. 2y minus 80 has to be equal to y plus 9, and the reason they have to be equal to each other for this quadrilateral to be a parallelogram, the diagonals must bisect each other or have equal lengths. So the other equation is 2y minus 80 is equal to y plus 9. First, I'll solve the equation that I did here in red. This equation, there's a couple ways to solve it. First, I'm going to do two things here in the first step. I'm going to subtract 8x from both sides, which is going to get the x on the right of the equation. And at the same time, I'm going to add 24, not 12. I just wrote 12 there, but that should have been a 24. Adding 24 to both sides, 12 plus 24 is 36. On the right-hand side, 10x take away 8x is 2x. I next divide each side by 2. The 2's on the right divide out, leaving x being equal to 36 divided by 2, which yields 18. Therefore, the value of x for this to be a parallelogram is 18. The other equation is a little bit easier to solve. Not that the one in red was hard, but in this case, I'll subtract y from both sides of the equal sign. That'll eliminate the y on the right-hand side. 2y take away y is y. Then I will add 80 to both sides, which is going to give me on the right-hand side 89. So the value of y to make this a parallelogram is 89. So the two solutions here, x is equal to 18 and y is equal to 89. In example 2, we are asked to determine if we can prove that a quadrilateral is a parallelogram. Here in the orange example, part A, we are given that segment AD is congruent to segment BC, so that's one pair of opposite sides congruent, and we are told that segment AB is congruent to segment AC. Can we prove that quadrilateral ABCD is a parallelogram? Well, with what's given here, we cannot prove that this is a parallelogram, and for the given information, since it's talking about sides, we would have to have opposite sides congruent for this to be a parallelogram. So since we don't have all the information about opposite sides, we cannot determine that this quadrilateral is a parallelogram. And another way to put that is that we do not know that AB is congruent to DC. If we knew that AB was congruent to DC, then opposite sides are congruent, which means this would be a parallelogram. In example B, this red example, we're given the measures of three of the four angles of this quadrilateral by the polygon angle sum theorem. If we add all four of these up, it should be equal to 360. Now we have one pair of opposite angles congruent, so what we need to do then is find the measure of this missing angle, and I'm just going to label that x. So we know that 75 plus 75 plus 105 plus x is equal to 360. Solving this equation, when I add 75 and 75, that gives 150, and 150 plus 105 is 155. Should be 255, not 155. Then I subtract 255 from both sides. And when I complete that subtraction, I end up with the missing measure as 105. So since I can show that opposite angles of this quadrilateral are congruent, then yes, I can determine that it is a parallelogram.